everybody, welcome back to the LearnAPChem series here at LearnAP. Now before I get going, I want to remind everybody that we are starting two new series on AP World History and AP US History starting October 9th, Columbus Day. So be on the lookout for that new content. In today's video, we're going to talk about gas laws. So we'll go over Boyles Law, Charles Law, gay-Lussac's law, Avogadro's principle, the ideal gas law using density, STP or standard temperature and pressure, and partial pressures. As usual guys, if you have any questions on this video, be sure to leave a comment, or you can ask in our live streams that we do for chem every Sunday from 5 to 6 p.m. Eastern. Other than that, we'll get started. Alright, so let's start by talking about a few gas laws. And there are a couple you should know. The first is known as Boyles Law, and this is saying P1V1 equals P2V2. Essentially, a gas's pressure is proportional to 1 over its volume, or pressure is inversely proportional to volume. Similarly, Charles' law states that V1 over T1 equals V2 over T2. Now this one is saying that a gas's volume is proportional to its temperature. The gay-Lussacs law says that P1 over T1 is equal to P2 over T2. So our pressure is proportional to our temperature. So here, volume is proportional to temperature, as is pressure. Now Avogadro's principle says that V1 over N1 equals V2 over N2. Now this one is saying that the number of moles in a gas is proportional to its volume. Now you can also think about this as saying if two gases have the same pressure and temperature and the same volume, they will then have the same number of moles, which should make intuitive sense. Now these can also be used in calculations in addition to sort of understanding these conceptually. So here's an example. One gas was found to have a volume of 23.4 liters and contains 2.41 mole. If another gas contains 5.32 mole and both gases have the same temperature and pressure, what is the volume of the second gas? So before I get going here, this sort of note I have here, same temperature and pressure, is important because all of these up here are assuming that the variables not included are the same. So here for Charles' law, we're assuming that our pressures are the same. Here in gay-Lussac's law, we're assuming that V is the same. So that's just an important note. But in most of these questions, if it's not explicitly mentioned, you can assume that you're supposed to think that they have the same temperature or pressure or whatever. So here, we just want to plug these into Avogadro's principle. So our V1 is 23.4 and our N1 is 2.41. Now, our V2 is unknown, just V2, and our N2 is right here, 5.32. Okay, so dividing this first one out, we get 9.7095 times 5.32, because we're just solving for V2. And if we do that multiplication, we end up with 51.6547. We need the right amount of sig figs, which here is just 3, so 51.7 liters. So problems like these are pretty easy. You essentially have one unknown, you just plug the other three values in and solve for the one that you don't know. Alright, so now let's talk about the ideal gas law, or PV equals nRT. Now you might hear this said phonetically as pivnert, and that's just basically talking about that, PV equals nRT. So if you hear someone talking about pivnert, they're talking about the ideal gas law. Now, important note about units here. P is pressure given in ATM, and R is 0.08206. Now these ones are flexible. You could change P to be pressure in millimeters of mercury, but then you would have to change R. So for right now, just memorize pressure in ATM, this is your R, and if you have pressure in some different units, you're going to want to convert to ATM. I mentioned the conversion factors in our video, Common Facts You Should Know. And so you can go ahead and check that video out if you want to sort of memorize the conversion factors between pressure. Volume is given in liters, and that is not flexible, so always in liters. N is the number of moles of gas, and T is our temperature given in Kelvin. And this serves a very important function in that Kelvin is always greater than or equal to 0, while the same is not true of Celsius. So if we had, say, -5 degrees into T, we would then get either a negative pressure or negative volume, which doesn't make any sense. So T, temperature, and PV equals nRT is always in Kelvin. And to go from Kelvin to Celsius, just add 273.1 to whatever degrees you are in Celsius. Okay, so that's all that's basically saying. You might also see this as 273.15. Doesn't really make a difference. Either way is fine. Now I talk about this being the ideal gas law. What this essentially means is we're assuming that there's no attractive or repulsive forces between the actual atoms in the gas, and that these atoms are not hitting each other because their atoms are so small. And so this is sort of a simplification. We'll talk more about ideal gases versus real gases later, but for now just know that this is in fact the ideal gas law. We're making some assumptions to simplify. Now unless you're told otherwise, you should assume that a gas is an ideal gas for AP chemistry. Alright, so let's talk about the alternate form of the ideal gas law, and this says PM equals dRT. Now what does that mean? Well, P, R, and T are all going to stay the same. So P is going to be given in ATM, T is given by Kelvin as usual, and R is our same constant from before, 0.08206. Now M here is molar mass, which is as usual in grams per mole, and D is the density of the gas, given in grams per liter. So sometimes you might be asked, given a gas is, so you would say like CO2 has pressure of 5 atm and temperature of 300 K, what is the density? So if I look at PV equals nRT here, I don't have anything for density, so that's where this form comes in, where I could simply just plug in my knowns into PM equals dRT and solve for D in this question, where I couldn't do that for PV equals nRT. So this is a very useful thing to know for the AP test. I definitely recommend that you memorize this formula and be familiar with it. Alright, so now let's talk about a concept that you guys should be familiar with, and this is called STP. And STP, as I alluded to earlier in the video, is shorthand for standard temperature and pressure. Now, at STP, temperature is 0 C, or 273.15 K, and our pressure is 1 atm. Now a quick shortcut is that at STP, the volume of 1 mole of an ideal gas is 22.4 liters. And this comes out from PivNert. So at STP, we know our pressure is just 1. Our V is unknown. Our N we're saying here is 1. R 0.08206 times T, which is 273.15. And if I multiply this through, I end up with 22.4. So this is a good thing to know, because a lot of times you'll be given that a gas is at STP, and if you know this, that for 1 mole of an ideal gas at STP, our volume is 22.4 liters. That's a quick shortcut. But do note that this only works at STP, so don't try this at something that isn't STP. Alright, now let's talk about partial pressures. And you should first be familiar with Dalton's law of partial pressures, named after your favorite chemist, Mr. Law of partial pressures. Now, Dalton's law of partial pressures, not to be confused with Dalton's law from before, says that the total amount of pressure is equal to the partial pressures of each gas. So sort of an example here, if hydrogen gas exerts a pressure of 1.3 atm in a mixture, and oxygen gas exerts a pressure of 0.2 atm, the total pressure of my mixture is 1.3 plus 0.2, the partial pressures of each gas, or 1.5 atm. Now the pressure exerted by a gas is given by its mole fraction times the total pressure. And a mole fraction is just the number of moles of gas X, or just some random gas, all over the number of moles of gas total. So if I had, in this example, say 5 moles of H and 1 mole of O2, my mole fraction for O would be 1 over 1 plus 5. Now note that that's probably not going to actually work in this example. I just sort of made those up. But here we do have an example problem. If there's 3.24 mole of gas in a sample of gas containing oxygen and carbon dioxide, and the total pressure is 4.26 atm. If there's 2.88 moles of CO2, how much pressure does oxygen exert? So take a second to think about this, pause your video, unpause when you think you found the answer. Okay, so in this example, we're given that there's 3.24 moles of gas total. And our total pressure is 4.26 atm. So if I want the pressure of oxygen, I first need to find the amount of moles of oxygen, because I need to find my mole fraction. So 3.24 minus 2.88, remember there's only 2 gases here, oxygen and carbon dioxide, so whatever isn't carbon dioxide is going to be oxygen. So here I simply get that my amount of moles are 0.36 moles of oxygen. Because remember, whatever moles isn't carbon dioxide is just going to be oxygen. That's where this comes from. Alright, so now I want to get my mole fraction. So 0.36, that is the moles of oxygen gas, over the moles total. So here I'm just going to divide this out, and I get 0.111 repeating as my mole fraction. And I can just simply multiply that by my total pressure, and this is going to give me the partial pressure of oxygen, which is 0.473 atm. Alright, so that brings me to today's challenge problem. A mixture contains 3.24 moles of gas and is held at STP. If the mixture contains 2.12 moles of oxygen, 0.53 moles of carbon dioxide, and the rest hydrogen, what is the volume of the sample? The solution to this problem is on our website, learn-ap.com, and I'll also put a direct link in the description. If you guys found this video helpful, please hit that like button. That lets us know that we're putting out content that's helpful to you. And be sure to subscribe for future content. Like us on Facebook and follow us on Twitter so you never miss a live stream. And those are going to be from 5 to 6 p.m. Eastern for chem. If you guys are looking for other resources to help you learn AP Chem, check out our resource recommendation video on our channel. Leave a comment if you guys are still confused about anything, or also any other comments on the video in general. Other than that, I want to thank you guys for watching, and I'll see you in the next video.